over here, right at the top. Okay, we will induce a voltage over there. All right.
You are now muted.
Okay, the next thing is the voltage is coupled to L1. L1 is the tank circuit here. All right, the tune circuit, the L1. Okay, you couple the voltage is coupled to L1 and is of such polarity that you will further forward bias Q1. Okay, continue to forward bias Q1. With more forward bias current, I mean the so-called point number 5, right, rise up, you will reach a steady state when of course, the transistor will come to a saturation, the maximum current. Okay, maximum current flow. Okay, what happened when maximum current flow? Of course, it will become steady. Of course, that's a max already. You can't go further. All right, the induced voltage drop to 0. And no more coupling occurs between L1 and L2. Okay, so in other words, C2 here there's no more coupling, and then what happens next is very important. Okay, at this juncture, C1 will charge to a positive potential on the top plate. Okay, hold on first. We come back to the circuit. We are talking about capacitor here. You will start to charge. All right, and the top plate means over here. The top plate will start to charge. All right, to positive. Okay, you follow me first. Then of course, with no more number 8, point number 8, quite a fair bit. You follow me a while first. Later we can summarize. With no more induced voltage across L1, the tank action takes over the following sequence. Okay, that means from that point onward, something is happening only here. Okay, the L and C circuit here. So I want you to focus on here. Now we are going to talk about this. But we just started by saying that capacitor has charged up and the top plate is positive. I just draw here. Okay, we continue first. So I just want you to focus on this one. Now the action is all there. Okay. Now, so of course, as you know, capacitor charge and discharges, right? Correct. So the tank, just now we mentioned the tank action will take over. What is the tank action? Let's take a look. Okay, C1 will discharge in an anti-clockwise direction. Okay, that means come back to here. C1, okay, it will charge. After it's fully charged, it will discharge. It said anti-clockwise. Okay, discharge through the inductor in the anti-clockwise. Okay, follow me first. Choice, because this one quite a fair bit. Okay, so when the current flows through the L1, L, there is the circuit we're talking. All right, there is a flux building or magnetic field. All right. So of course it charges to a point when current from the capacitor C1 stops. Then now this so-called inductor, the L, will also start to collapse because just now it was building when the current flowing through. Okay, so you continue to flow in the same anti-clockwise. Okay, this new current changes C1 to become positively charged at the bottom plate. All right, so what happened is they're trying to tell you that when this magnetic field across so-called the L1 collapse, the current will continue to charge this way. All right, the capacitor. So just now it was a top plate. Now it becomes a lower plate that is positive. And then opposite, okay? So-called the polarity has changed. That's what it means. So when the polarity change, of course, something also happened. Let's take a look. Continue first. All right. So collect current just now continue flow and anti-clockwise. Yeah, just mentioned. Okay, become positive charge at the bottom plate. Just I also draw there already. So since C1 is now negatively charged on the top plate, Q1 turns off. Let's come back to here. Okay, if now the lower plate is positive, this is negative. Okay, if this is negative, this point is going to the base, it will turn off the Q1 because the Q1 need a positive voltage to turn on, but now it become a negative. So negative comes to the base of Q1, the Q1 will turn off. Okay, switch off already, switch off. Okay, then we see what happened. Quite a lengthy one, but no choice to go through. Okay, so I just mentioned Q1 cuts off because now the C is negatively charged. All right. Now the tank action take over again. Okay. Except that C1 discharged in the clockwise. All right. So very naturally, we come back to here. Just how it was this way, right? I start to charge. Then after C1 gets fully charged again, they will discharge. But this time around, I discharge this way, clockwise. All right, just now was anti-clockwise, now clockwise. Okay, I hope you're following. I'll summarize a bit later. Okay, so when this happened, of course, you realize that there is the output of a sine wave. All right, oscillating on the positive cycle, then the negative cycle. So that is what it means. All right. Okay. Now, okay, maybe I want to just focus on the LC here to clarify. Okay. I summarize for you. The rest, hold on first. The rest not so critical. Actually, the main action is over here. All right. I try to draw this inductor. Okay. Oops. Okay, I try to explain a bit more here what is happening. Because when you read, you may not get it. So, okay, the main action happens over here, the L1 and the C1. Okay, that's why the name of this oscillator, they call it LC, because these two components is the two main actors that give us the oscillation. Okay, when I say oscillation means here at the output, you get this sine wave going on. Okay, just now the initial part is capacitor was charged, fully charged like that. Okay, this manner. Okay, so the current flows this way, so-called anti-clockwise. Yeah. Okay. Okay, you can take it that the output voltage here, you have a positive waveform. Example, you follow me first. Okay. Maybe during the anti-clockwise, I have a positive cycle at the output ready. Okay. But there are changes, right? Why? When the capacitor is fully charged, what happened? It will discharge, right? It will discharge, right? When it discharges, what happened? The so-called the inductor will build a magnetic field. You know that capacitor store charges, magnetic field is stored by inductor, or it's some form of energy. Okay, so what happened is after the discharging, next moment, the polarity of the capacitor change. Now this side become positive, this one become negative. All right. Okay. So again, when it becomes fully charged in this manner, it will discharge. But this time around, I discharge, right? anti-clockwise this way. Okay? And so the first time I discharge this way, and after I'm fully charged again, I just now mentioned the positive is here, and I discharge, but this time anti-clockwise, or rather clockwise. So you can say that when I am discharging with this positive sign here, discharging in a clockwise manner, you can see another wave, half of the wave at the output. Okay? Then this action will keep repeating itself. So that is why you can have a continuous nice oscillation or sine wave at your output. Okay? So it's just charging, discharging, and charging and discharging polarity changes. And that's how you get your output sine wave. Okay? Yeah, I know the so-called the steps is quite a fair bit, but I want to bring your attention to this. So this inductor and capacitor circuit here, we call it a tank circuit. Okay, T-A-N-K, tank over here. All right. Sometimes, as I mentioned, they also use the word tune. All right. And sometimes they say it's a LC. They all means the same thing. Okay. I pause for a short while just in case anyone wants to clarify anything. Any question up to here for the operation of the LC oscillator or tank circuit? Anyone need clarification or have question for me? As I mentioned, the main action is the tank circuit, which make up of the inductor and capacitor. Oh, that's the main action. So you can imagine the charging and discharging of capacitor and polarity of changes, and that's how you get the output of oscillation. Okay. Any question? If not, we pause for a few minutes before I go on to the next one, which we call the RC oscillator. But they don't have high frequency, up to 1 megahertz only. For this tank circuit, you can go up to 500 megahertz. Okay, can? Maybe 2 minutes. And then I resume, but if you have a question, you can ask me now or later also can, up to you. Any part you want me to repeat? Anyone? Okay. So I resume in 2 minutes time to talk about the RC oscillator.
Just the thing of the
You are now muted.
Oh, sorry. I repeat again. I didn't know. Sorry. I repeat the whole thing again. Yeah. Okay. Let me delete first. Okay. Sorry about that. Someone told me I think so. Okay. We are going to the second type of oscillator. Here we call it a phase shift oscillator. All right. Sometimes you also call it a RC oscillator. All right, because of some components that you see in this circuit. Okay, we run through the components in the circuit first. All right, same thing as usual. We always have biasing for the transistor here at the base, done by the RB. Okay, that is to bias the transistor base. Of course, to turn on or turn off the transistor Q1. Always we need biasing at the base. I mentioned to all of you before, if you don't have a base current, the transistor is switched off. Okay, like a switch is off, not working. All right, so you need to send some base current, very small base current in microampere, but it will turn on the transistor. I just refresh. You're wondering why every time we need to bias it. Okay, that's the purpose. So RC, continue with the component. RC will be low impedance now. All right, over in this circuit, as usual, your emitter also has some biasing by RE. All right, and then same as just now the LC circuit, you have another capacitor here for improving the AC gain, and of course, Q1 does a very important job, amplification, okay, increasing the output. And then the three pair of main actors over here, I call it actors because just now there was LC, here is RC. Okay, there are three stages of phase shift circuits used here, O1, to provide 180-degree phase shift. Okay, can you all look here? What they mean is this one pair, this one circuit, another RC, another pair, and another pair. All right? Okay, so there are three stages. Then you are wondering, okay, three stages, and they tell you that the three stage will give you 180-degree phase shift. Very interesting. So some of you may ask then, one stage will give you how many degrees of phase shift? That is a question maybe I want to pose to you. Can someone make an attempt to answer this question? There are three RC circuits in this phase shift oscillator. The three stages of RC circuits give you a total of 180 degrees phase shift. So my question is, what about one circuit? How many degrees phase shift will you get? If three give you 180, one phase shift circuit will give you, or one RC phase shift circuit will give you how many degrees? Can someone make an attempt? Or I rephrase it. The three stages give you total 180 degrees of phase shift. Then I want to know one stage, how many degrees phase shift will you get? Anybody? Zhen Xian, you want to try? Anybody wants to try? One stage, how many degrees of phase shift will you get? If 3 gives you 180, 1 will give you how many degrees? Okay, just say 180 is for 3 stages. Yes, you're right. 180 divided by 3. Yes, correct. So you will get 60 degrees phase shift. Yeah, thank you. Correct. Thank you very much for the answer. Okay, so he's correct. Let's go back to the part here. All right, so 3 stages. So one stage will be 180 degrees divided by 3. Okay, so one stage will be 60 degrees actually. Okay, 60 degrees. Yeah? Okay, so now you know why there are 3. Because each one is 60. Okay, so you shift 3 times, you get 180 degree phase shift. Excuse me. Okay, Ken. So I explained this part. So at least you know why there are 3 stages there. So each stage actually give you 60 degrees. Okay, Ken, thank you. Okay, now we look at the operation, just like what we have seen, but this is much shorter here. Okay, our observation started by some noise in area and transistor. So of course there's changes in the base current. Just now I mentioned you must have base current. And then of course the amplification can take place. The transistor will switch on. Okay, which gives us a 180 degree phase shift. Okay. And then this phase shift is fed back to the base. Okay, through the 3, there's the 3 main actors, the 3 RC circuits. They use one network circuit. Okay, it's because of this three-stage RC circuit is turn or rather switch back the signal with a 180 degrees phase shift. Okay, over here. All right, so that the feedback signal at the base of transistor will produce a positive. Okay. So of course, because of the 0-degree shift, oscillation will start to build up and then it will continue as sustained. All right. Now I want to bring you back this, what I just said, the operation of this phase shift oscillator back to the block diagram this morning. This is exactly what happened. This is exactly what happened here. Okay. Okay, this whole block diagram applies to the RC, the circuit we just briefly talked about just now, just only. Okay, so you have an input wave like this, right, going through the amplifier, but this amplifier inverted it for you because there's a 180-degree phase shift. You get this waveform now, right? But this waveform is being fed back to your amplifier. Just now same, we are talking about the same thing. Now, then you go through this feedback network. Now I'm trying to relate you to the circuit. Now, this feedback network now is what? It's actually the 3 stages of RC, right? Circuit, right? Which we have in the circuit just now, yeah? So these 3 RC circuits or stage of circuits will invert or produce another 180 degrees phase shift. And then you get back a waveform that is to sustain the oscillation. This is exactly what it meant for the network. I relate you to the RC so-called oscillator. Okay, now go back, we take a closer look again. So if you follow me with the block diagram, you realize that, this is the feedback. This is the feedback network. Okay? Okay, this is the one that introduced you the 180-degree phase shift. But it introduced it to make sure that it's same as the input in phase. Okay? Then, so that block diagram is helpful to come back to relate to here. So that you, okay, this whole block here is actually the feedback. Yeah. Okay, whatever output is coming back to the base. All right? Okay? Then of course, finally your V out here, you will get a very nice continuous sine wave right at your output. All right? And okay, here same thing. You do have a formula for calculating the frequency of oscillation. Now every time we talk about oscillation, there must be frequency, right? Just like your power supply, right? 230 volts, 50 hertz, right? There's oscillation. AC is oscillation. The moment you have oscillation, we calculate frequency. So over here, the formula is such: F equal 1/2 pi RC square root 6. Okay, and the unit is hertz. So take note, this could be asked during your exam. Just take note. After all, there's not many formulas. So yeah, just take note. Okay, can any question up to here? That will be the end of topic 5, and we are going to 6. Okay. Okay, if no question, we take a very short break, 5 minutes. And then I will go on to the new topic. Any question first before I pause for 5 minutes? Any question for anybody? Any question? If not, then we resume in 5 minutes. Okay, then we take a very short break. Then I will go on to the new topic because next Monday is a holiday, so I won't see you on Monday. That's why I think it's good for us to start on the next topic first. Yeah. Okay, see you in 5 minutes time.
Back to that.
I am back. Okay, let's continue. First of all, I would like to do a check whether you still hear me and see the screen before I start. Thank you. Jessica, can you still hear me and see me? Just a check before I start on this new topic. Okay, Ken, thank you very much. Okay, I will continue to the next topic. All right, this topic, of course, the title is filters. All right, you will still see waveform like the sine wave and so on. So you're related to what you learned earlier on. Okay, first thing, introduction first, a filter circuit. Okay, here the word filter, I think to you, maybe in general, the word English means what? You want something to retain something and discard something, right? Okay, like you want to choose something over something, so you filter off. All right. Here, same thing actually applies. Okay, so here they say I want to select signals with the frequency that I wanted, the desired frequency to go past the circuit. All right. And of course, I reject those unwanted signal. Okay, same like in your daily life, you choose something over something, right? I want this, but I don't want that. So it's like filtering. Okay, here it does the same, because but here they talk about frequencies. All right. Okay, let's do a quick look at this block diagram, which could be helpful for you to understand it quickly. Okay, for example, we talk about a low pass filter right in the middle here. And then you send two sine wave, for example, all right, with two different frequencies. Obviously, you saw one is 10 kHz, one is 100 Hertz. Okay. Now, being a low pass filter here means low pass means they are talking about lower frequency can pass. Okay, so the word low pass means low frequency I want allow it to pass. I will stop the high frequency. Okay, so if having understand what I just mentioned or said to you, you obviously know that only the 100 Hertz will go past. Okay, because I'm using a low pass filter, which only allows low frequency to pass, comparing between the two. Okay, the lower frequency will allow to pass. And then of course the 10 kHz will not able to go through. Right? Okay. All right. Same for the high pass filter, it just works the opposite of a low pass. So now the high pass filter means higher frequency will be allowed to pass. Okay, and I rather reject low frequency. So again, the same two frequency is sent in at the input. One is 10 kHz, one is 100 Hz. But now, because it's a high pass, I will allow the 10 kHz to go past or go through. All right, and then reject the 100 Hz, which is the low frequency. Okay, so in general, that is what the low pass or high pass filter does. Of course, all these are being used in application in communication and so on. Okay, here we move on and they mention that the filter has two bands of operation. They call pass band, stop band. Okay, actually this word also is like self-explanatory, because pass band means the particular band of frequency is allowed to go through. Stop band, the particular band of frequency is being stopped. Okay, so in other words, these two is the opposite of each other. Right? Okay, I think there's a very quick sentence here that describes it. Same as what I just told you. One will allow it to pass through the pass band, that's why they call it a pass band. And one will stop it, that's why they call it a stop band, or will cut it off. Okay? Yeah, they are both actually opposites. Okay, we move on. Okay, figure 2 show you so-called the response curve of a filter. All right, now we take a closer look. What is it about? Okay, so first of all, they say that the output voltage is greater at low frequency. Before we talk about it first, let's identify the X and Y axis first. The Y axis is voltage, output voltage. X axis is in terms of frequency. Okay? Okay, before we start. Okay, so to understand this statement, it says that the output voltage is greater at low frequency. Where is our low frequency? Around from 0 here onwards. The low end. All right, around here. But at 0 frequency, the voltage is maximum. That's why they say when the low frequency, voltage is higher. But as your voltage drops or frequency get higher, your voltage drop, right? Right. So that's how the curve goes up. Okay. All right. So yeah, this is what I mean by this one. Voltage greater at the low frequency. One more time. You see Vmax, maximum voltage at 0 frequency, very high voltage, but low frequency. Okay. Of course, then they say, oh, this voltage will decrease. Yes, correct one. The voltage will go down as your frequency increase. Okay, until let's say your frequency here is very high, but your voltage drop almost to 0, example. Okay, so then this is how the curve works first, before we move on. Now, at a certain frequency, they call FC. All right. All right, the output voltage of the filter is this is 70.7% of the max. Okay, we are talking about a certain frequency here, which is then the cutoff frequency. Okay, so at this particular frequency, they say that you bring up this and you go here across and you get about this value. All right, or 70.7% or 0.707 Vmax. Okay, at this so-called cutoff frequency. Okay, then this is what here I try to describe to you and at the same time relate to the diagram. Okay, Ken? Okay, here they mention any frequency where voltage fall below 70.7 of the maximum voltage will be rejected. Okay? Okay, so anything after the cutoff, we don't want. All right, we doesn't want. Okay? Any question? So if you see the word bandwidth here, that means from 0 to FC is what I wanted. All right? After the cutoff, no more. Those frequency I don't want. That's why they say cutoff frequency. Up to here only. Okay, up to here only. 0 to FC. This is the range or the bandwidth that I wanted. After cutoff, I don't want. Okay? Okay? So of course here they describe to you the range of frequency, we also call a bandwidth. Okay? For example here 0 to let's say 10k hertz here, example. So this become my bandwidth. Okay, my range of frequencies. But here means 0 to 10k example. And it's known as a bandwidth. Alright? Okay? Question for the first explanation of a filter, so-called the frequency response curve. Wait, I pause for a while in case anyone. Any question from anyone regarding the paragraph and how you relate to the response curve? Any question? No? Okay, then I continue first. Okay, we move on. Now we look at the different type of filters, right? Okay, first thing first. The first type is called passive filters. Of course, when you hear the word passive, means no power gain. Okay, and then of course the opposite of the active, passive we call active, then with some power gain. All right, so this is the first explanation of two types of filters. Take note first as we go on to describe the rest. Okay, so here we start out with passive filters first. They say formed by the very basic resistor, capacitor, and inductors. Okay, all these components I believe you have seen before. All right. So they mentioned the output signal power is usually lower than the input power. Okay, in terms of power, the output power is lower. Okay, usually lower. Okay. All right. With that, we start off with the low pass passive filter. Let's take a look. Okay, the first one, low pass passive filter. How is it connected up right in front of you here? Okay, with a simple R resistor and then a capacitor. Okay, and obviously input on your left and output on your right. Okay, here on the right hand side is your response curve. Just now we mentioned, just now earlier on described. Okay, so for the low pass, it looks exactly the one we saw earlier on. Okay, first thing I bring you back to the point where there's a cut-off frequency, we call FC. Okay, now for the low pass filter, the cut-off frequency example is here. All right, okay, here. FC. All right. Now you saw the word here from 0 to the cut-off frequency. This frequency is what I wanted. That's why they say pass band. I allow this range of frequency to pass. Yeah. So obviously, if I tell you pass band is allowed to pass, the stop band means after from the cut-off frequency onwards, I reject. Okay. So only this frequency at the pass band is allowed to pass. Okay, that will describe your RC low pass passive filter. Okay. Any question? Okay, here there's a simple calculation for your XC. XC, remember? You know, remember what XC? Your capacitive reactance. Okay, AC we call it reactance. I use XC, or C for capacitor. So you are calculating the reactance of the resistor. Okay, at the point when your input is 0 hertz, no frequency, nothing at all. Okay, then obviously your capacitor is super large, the value. Okay, the reactance of the capacitor, which is given by this formula, 1/2 pi FC, the cut-off frequency multiplied by your capacitor value. Okay, can? So take note of this. Of course, as the frequency increase, just how we mentioned, what happened? Your reactance drop also, of course. And of course, followed by your V out. Okay, also decreases. Look at this curve again. Look at the frequency. Okay, from left to right, as the frequency increase, your voltage start to also drop, right? Smaller and smaller as you go higher frequency. Okay, that's what it meant here, just in case. Okay. Okay, until the cut off for that over here. Okay, it's reached. Okay, so output power equal to the half of the input power. All right, here they mentioned that. So at cut-off frequency, there's some calculation here. Just take a quick look. Okay, XC they say actually equals to the resistance R. Okay, also it's the same formula applies here. Okay, same formula applies here. Since they are equal, this formula can be used. Okay, and then we calculate the cut-off frequency. Okay. So actually the R and the XC both are equal. All right, that's why you can use the same formula here. All right, XC and R also can be equal to the same formula. And this one is for calculating your cut-off frequency. Okay. Question any first before I move on? Any question? How come? Let me see. Any question regarding the low pass? Oh, okay. Thank you for reminding me. I accidentally clicked on that. Thank you. Thank you. Okay. Any question before I continue? For your passive low pass filter. Okay. So to sum up very quickly, this low pass filter only allows low frequency to pass. All right, as you see from the response curve. Yeah, over here, one more time. Okay, so the pass band is over here. So just from 0 to the cut-off frequency, this one I pass. Yeah, after that, stop. That's why they I will not allow. That's why they call it a stop band. Okay, so these are the two components, very basic components that form the filter. All right. Okay, let's do some example here. Okay, what is given the resistor value 100 ohm? What is given the capacitor value 0.005 microfarad? Okay, and they want us to calculate the cut-off frequency, which is FC here. All right. Okay, cut-off frequency is this one. And formula given just now above, yeah, before we come here. So this is a formula you have to remember, write it out, and of course, please be careful of the unit. Okay, the exponent. Micro is 10 to the power of -6. So I always remind all of you how to confirm, very simple, use your calculator, punch in all these, enter all these, and then make sure you get this answer. Okay, so frequency, of course, the unit is hertz. So here you get 318 hertz. Okay, this could be a possible question in the exam, but you'll be happy if it comes out. Not that difficult. The only thing is, my concern, and maybe your concern is, when you key in the values in your calculator. All right, just be careful. Or to miss out those units, micro, mini, and all that. The answer will really change. Okay, then I move on. So they round up. So low pass filter, they say what are the application here? Okay, filter used in audio. Okay, anti-aliasing filter, conditioning prior to analog to digital conversion. Okay, these are all the application of filters. All right. Okay, Ken. So if no question, we move on to the next one. We have done the low pass. So now we look at the high pass. Now, before I start, it's not difficult to understand these two because why? If you know the low pass, you know the high pass. Why do I say that? Because they are just the opposite one. Okay, why so? Listen, you see, just now you look at the circuit. Just now for the low pass, the resistor is here, but now they switch place. Resistor now goes down to here. Yeah. Okay. Can first observation. Okay. You swap place. Just now resistor was here at the capacitor, but now resistor move here, capacitor move here. All right. This one no change. Input here. Your output also here. No change. Now you look at the curve. You realize that, correct, it's just the opposite. Just how the curve was something like that. Yeah. Something like that. Yeah. So now the other way. Why? Now you see where is the stop band? Low frequency. Now after the cut-off frequency, which is high frequency, I say pass band, which is what I wanted. I allowed higher frequency to pass. That is the reason they call high pass filter. So it works exactly the opposite of the low pass. Okay, low pass, I allow low frequency to pass. High pass filter, I allow high frequency to pass. Okay, so with that in mind, I think you don't have to worry too much, because as I mentioned, if you know the low pass, the high pass is just the opposite. Okay? So same thing, you see, they tell you the same thing. Right? Okay? Exactly the opposite. Alright? So don't have to worry. Of course, there's a formula again, same thing for you to calculate your cutoff frequency. You still use the same. Alright? Okay? 1/2 pi RC. Okay, let's take a look at the example here for some calculation. Again, same thing, they want you to calculate the cutoff frequency. What is given? Capacitor value 0.047 microfarad. Capacitor given, resistor also given 10k ohms. So using the formula, I just circle here, you just come here and then put in all the values and watch out for this. Alright, 10k is 10 to the power 3, micro is 10 to the power -6, and then you should get this answer in hertz. Okay, because we are talking about frequency. So please use your calculator, own time, own target, key in everything nicely, and confirm your answer. Okay? Alright, same thing for high pass filter. Of course, they still use for audio, but now I want high frequency, those screeching sound, very high pitch one. For example, in the audio world, they call it a tweeter. This will take out all those high frequency. Music, right? Some instrument, the frequency is very low. Some instrument, the frequency is very high, example. Okay, so I can use all these filters to either allow you to pass or stop it. Okay? Also for AC coupling, audio power amplifier, yes, just mentioned, no loudspeaker coil, same thing. All these are related to your audio equipment. Okay? Okay. Take note of the application. Okay, band pass. Let me see whether we have time to move on to the rest first. I want to see how much more to go. Oh, okay. Okay, so the band pass is the last filter that we are talking about this morning. Okay. All right. You saw the low pass filter. You saw the high pass filter. Now, easy to understand this. So now, how to understand the band pass? Okay, first of all, you're asking what you mean. Okay, so band pass is, I don't want the low frequency, I don't want the high frequency, I want the frequency in the middle. Okay, then maybe it sounds better. Okay, that's why they say allow between the two specific to pass. All right. Okay. Reject. Okay. So with that, we look at the circuit again. Now, of course, you expect to see more. Rather, you can see one low pass, one high pass, right? Where is it? Okay. This one we just went through just now. Just only. This is a high pass. And then this one you know is a low pass. Yeah. Okay. Okay. Same thing, no different input here. A right hand side output. So if you see both high pass and low pass inside a circuit like that, straight away you know it's a band pass filter. Okay, the components of arrangement. Okay, I just mentioned this is a low pass. This is a low pass filter. You can relate back to the earlier one. Right? And this is a high. Okay, this is a high. Yeah? You can relate back to the diagram above. I just write out first. Okay, Ken. So now we look at the characteristic curve of this or response curve of the bandpass filter. And then you realize, oh, correct. So this is what it meant. Okay, follow me first. Now this is the response curve. All right. So if I want to put it in perspective, the rising one is actually the high pass filter. Yeah. The other curve will be the low pass filter. And these two add together will give you this like a mountain or hill. Okay, I point to you. If you relate back to your diagram earlier on, this is your high pass filter. The curve. Okay, the up slope. And then your down slope is relating to your low pass filter. Yes. So putting them both together, I have this so-called like a hill or mountain kind of shape. And then now the next question, I think all of you will be asking, so which frequency are we going to allow to pass? Which I told you is here. All right, the middle. Okay, that's why we call band pass. All right. So the stop band will be here at the low frequency. From here to this F1. Right, I don't allow to pass. Same, I also stop here. After F2 onwards, I also stop. So I only allow F1 to F2 allowed to pass. Okay, so the middle range of frequency. That again come back to the word band pass on, which I have clearly drawn here for you, how you identify it. Okay, I don't want the low frequency and neither do I want the high frequency. I want something in the middle. That is how this circuit is connected, and this is how this response curve relate to the circuit. Okay? Any question first before I pause or I stop? Any question? Okay, if not, then we cover a bit more, and then this one is just application. Okay, here they mentioned to you wireless transmitter, receiver. Now, because in all these communication equipment, they use a range of frequency. Okay, just like a radio, you say FM radio, example, FM radio will have a range of frequency and so on and so on. So they will probably use a filter to so-called filter out those frequencies that I don't want and only one certain frequency, just like you're tuning to radio. Okay? Yeah. And any question? If not, then I will stop here. Any final question? Anyone? Any questions?
Almorzar. Bueno, no quieren los tacos que preparó mi mujer. Gracias.
Amigo, ¿tú sabes qué? La vaca va de
Okay, if you have no question,
Dios mío.
you may log off. Then I will see you not on Monday, because next Monday is a holiday. So I'll see you next Wednesday. Okay? If you have questions, stay back and ask me. Or also you can contact me also if you really need to ask me any question after the session. Okay? Okay, thank you very much. And have a great long weekend.
Lại là chăm sóc kỹ thuật đồ ở shop. Vì
Không chị bạn.
Earbuds.
Tôi có chuyện.